Hello, everybody, and welcome to another class of ATMO 620. I hope you're all doing well, and I hope you're following all the classes and that all the material that we are covering is clear. Now, in the last few lectures, we saw a variety of topics. We started off from some basic thermodynamics, and we talked about the ideal gas law, and then we moved on talk about the first and the second principle of thermodynamics, and we saw some of the consequences of these principles. And then last time we talked about what I call moist thermodynamics, and this is usually a word that is used to denote thermodynamics when you take into account water vapor. Okay. And now that we've taken into account water vapor, we learn how to quantify the amount of water vapor in the atmosphere. We learned to compute its saturation, vapor pressure, and saturation mixing ratio, and yada, yada, yada. Now we can move on. We can take one step further and talk about what happens when water vapor condenses. What happens when you eventually reach saturation. And so today we will start our journey into cloud microphysics, which is the second part of this class. And in this journey, we will talk about rain and ice, hail, and many forms of hydrometeors. But today we will start with the basics. And so we will start with cloud droplets. Okay. So what happens when water vapor condenses? What happens when you reach saturation? Well, the short answer is you're going to form cloud droplets, okay? But stay with me because it's not that simple, okay? Obviously, because otherwise, this course would be finished already. So it's a little bit tricky, and today we will see all the different subtleties, and we'll learn to compute a bunch of things. Okay, so the first thing that I want to talk about is the fact that when we reach saturation, a phenomenon happens that is known as phase change. Okay, phase changes happen pretty much everywhere in physics. Okay, in many different systems, we do observe phase changes. Obviously, the phase change from vapor to liquid is the one that we're probably most familiar with, thanks to the formation of clouds. But there are also other phase changes, of course, other changes that could happen. One simple change that you're probably very familiar with is the change from the liquid phase, which is what we call water, to the solid phase, which is what we call ice. So whenever you want to make a cocktail and you want ice cubes, your fridge has to do that phase transition for you, okay? And it makes ice cubes that you then put in your cocktail. One other type of phase transition that can happen is the transition from vapor to solid, and this is something that we're not really that familiar with. It's not something that happens frequently in nature, at least as far as water is concerned. And one of the reasons why that is that it requires conditions and temperature or pressure that are not typically encountered at sea level. Okay, and so these processes are not they're not very common. Obviously, the opposite is also true. So, meaning that these phase transitions also work the other way. So some of the liquid can eventually evaporate. And that happens every time there's a thunderstorm. We'll talk about that at some point. Solid can melt back into liquid. So ice cubes can go back to being liquid water, which, again, if you ever had, something iced coffee or something, you're probably familiar with this. And also, the transition can also happen from the solid to vapor. If you've ever been skiing and you looked at someone sort of in front of the sun, sometimes you see that this person seems to sort of evaporate, right? You kind of see vapor around this person, and often this is exactly the transition from solid to vapor, because maybe this person has I don't know, snowflakes around their hair or on their clothes, and the sun just heats those snowflakes so much that some of the molecules evaporate directly. Well, they don't actually evaporate. Evaporation is a word that we use to denote the change from liquid to vapor. When solid to liquid is obviously melting, solid to vapor is what we call sublimate. Okay, vapor to solid usually we call deposition or direct deposition. The opposite is sublimation. Okay, and it's important to keep to bear in mind the fact that these transitions happen, because these transitions are what make the atmosphere particularly complicated. Because if it wasn't for these phase transitions, then it would probably have some Rayleigh-Bernard convection at the surface. It would be simple dry convection, for which many relationships can be derived quite simply, and life would be very simple, but also very boring. So, I don't know. Yeah, it's more complicated. There are more things to do, but it's also more exciting because there's more things to take into account, to learn, and to discover. Now, what is interesting is that, as this picture shows, water droplets are not. The story is not quite as simple as just water molecules sticking together and that's it. Phase transitions usually don't happen at thermodynamic equilibrium, which is kind of what we were thinking about in the past few classes. If you remember, we said, let's put some liquid in a box and you'll have some molecules leaving, some molecules coming back in, and eventually you reach equilibrium. In nature, that doesn't happen. You're not at thermodynamic equilibrium. And actually, what is interesting is that water droplets have a really strong surface tension. And this surface tension essentially keeps the droplets together, if you will, right? It forms the droplet. The reason why we observe this surface tension is that molecules, if we can draw a water molecule like this, molecules have, even though a water molecule is strictly speaking neutral, it does have some remnant of a charge. And so it does have some weak electric field around it, okay? And so if there are other molecules, right, around it, this molecule here will attract, right, these other molecules. So these will be attracted to this molecule, and likewise, this molecule would be attracted to the other molecules, right? This is kind of what, how liquids work. So if you're a molecule in the middle of a droplet, then you're attracted by everybody, and so you're not really moving because let's assume a very simplified case, but you're not really moving because everybody's pulling you with the same strength in all the possible directions. And so the resultant of all the forces is zero. But if you are at the edge, let's say that this is the edge of the droplet. Let's use some imagination because my drawing is terrible. So these are the different water molecules. In the middle, there's, it's empty. There's emptiness. This line doesn't really exist in nature, but it's just to give you the idea that this is the edge, okay? And there are other molecules around here. Now, these molecules here are attracted by some inside, some on the edge, to the right, to the left, yada, yada, yada. Molecules on the edge, on the other hand, they're attracted by this molecule, by this molecule, by this molecule, by this molecule, but they're not attracted by anything outside. And so the resultant of the forces is not zero, but it's a force that is pushing this molecule, let's use a color, that is pushing this molecule inside, okay? So this is what the surface tension is, essentially, is the molecules at the edge, they're only pulled inward, all right? And they don't have anyone to counterbalance this inward force. And that's why the droplet kind of sticks together, right? Okay, so Because of this surface tension, things aren't quite as simple as you might think. If it wasn't for this surface tension, whenever you reach saturation, then molecules of water vapor would stick to the droplet, and you'd condense, or you'd condense even more, right? However, because of the surface tension, there's like a wall, right? Let's say that this is the droplet. The surface tension here, that again I'm going to draw with a red here, this is creating, this looks like those, I don't know how many of you were alive in the 90s, but there were these commercials, like, they were like PSA commercials for HIV, and it was weird. They were like people with like purple contours. Anyway, probably most of you, if not all of you, weren't even born, so why am I bringing this up? So this surface tension is keeping this droplet together, and it's kind of creating a barrier. And so when water vapor molecules from outside feel, the desire, let's put it like that, to join the water molecules, so when we reach saturation, right, and there are so many water molecules that a lot of them will just want to stick to this droplet, water vapor molecules that they'll want to stick to the droplet. Well, they'll hit a wall, much like this animal here, this cricket or whatever it is, can literally walk on the water, okay? Because the surface tension is kind of bouncing it off, if you will, okay? And so what this means for the atmosphere is that you're going to need a lot of supersaturation, right? So it's not that you reach saturation and boom, you have your cloud droplet. You're going to have to reach a really high value of supersaturation. So meaning that there has to be so many water vapor molecules that essentially, even though this wall here will act to sort of bounce these away, the other water vapor molecules from outside, they'll push these molecules that are close to the edge. They'll just push them inside of the droplet, okay? So you need, a lot of molecules outside to push you inside to win this potential barrier, if you will. And so our intuition that you reach saturation, boom, you have cloud droplets, is not correct, okay? You could reach, you could actually need, so, you'd imagine that at saturation would happen by definition at relative humidity equals to 100%, right? But you don't typically have clouds here. If the world was perfect and super clean, you'd need values of 140% of relative humidity before you actually start to see a cloud. Is it easy to find 140% relative humidity on Earth? Absolutely not. And it's almost impossible to find it. So why are there clouds to begin with? If it's so hard, if there's this surface tension that bounces water molecules away. Well, the answer is that the world is dirty, right? So the atmosphere contains just a lot of small particles. And these small particles have an affinity to water that attract water molecules. So if the atmosphere was clear, you'd have to convince, all these molecules to stick together and to overcome the surface tension that they would encounter once 2 or 3 start to stick together. And so it gets really, really hard to push them together. But if you had, some kind of dirt that naturally attracts liquid water, water vapor molecules, these molecules kind of stick together, and this very slowly, this particle of dust or soot, pollen, sea salt, volcanic ash, it would become populated with these molecules, and essentially because these molecules, these water vapor molecules are sticking to this dirt particle, they don't feel their mutual repulsion, and they don't feel it until there's so many of them that they just stick together, right? and this would become just one droplet of water. Okay, it's a bit like suppose that Alice doesn't like Bob at all, right? They can't, right? They fight. They can't talk to each other, and so the chance of these two spending some time together are almost zero. But let's suppose that Alice likes Charlie, and Bob likes Charlie. And so even though Alice and Bob would not spend time together, Charlie could say, hey, Alice, why don't we meet today at 3 p.m. and we can go for a walk, and then call Bob and say, hey, Bob, why don't we meet today at 3 p.m. and go for a walk? And at the end of the day, at 3 p.m., Alice, Bob, and Charlie all meet and go for a walk. Okay, so Alice and Bob would have never done that. They would never have gone for a walk together. But because there's this middleman, Charlie, they can spend time together. So, Alice and Bob in this example are the water vapor molecules, and Charlie is, no offense to Charlie, but it's the dirt particle. So, and these particles are known as cloud condensation nuclei, which is often abbreviated with CCN because life is short, and so you'd often hear people just say CCN because it's just shorter. When this happens, that dust particles or CCNs create a droplet, okay, favor the creation of the droplet, you talk about heterogeneous nucleation. Heterogeneous means that you have different substances within the droplet. If, on the other hand, you don't have this dirt particle and your water droplet kind of was formed because the relative humidity was so high that these particles just kind of stuck together. In this case, we talk about homogeneous nucleation. Okay, this is possible, but it requires conditions that are not easily met on Earth. Okay, so interestingly, and maybe luckily or unluckily, I don't know how much you like clouds. I do like clouds a lot, and so for me, it's likely, not likely, luckily. Sorry. These dirt particles, I keep calling them dirt particles, which is not really the right term. These CCNs are usually wetted for relative humidities slightly higher than 100%. And so they can form clouds much, much more easily. Some of these are even wetted for relative humidities lower than 100%, which is why sometimes we have what we call haze. Okay, this is a picture of a haze day somewhere. As you probably guessed, yes, smog is also a contributor to these cloud condensation nuclei. And polluted environments have different CCN concentrations than perfectly clear environments. Pollution is not the only one, however, and so, marine environments have different CCN concentrations than other kind of environments, et cetera, et cetera. This we already said. Okay. What about ice nuclei? Well, what about ice? Okay, what about the formation of ice? Well, something similar kind of holds true for ice in that when the water droplet reaches 0 degrees Celsius or 32 Fahrenheit, please don't use Fahrenheit, or 273.15 Kelvin. In your head, you think, okay, it freezes. So yeah, you have an ice particle. Okay. Well, actually in nature, it doesn't quite happen this fast, right? And so often what you end up having is that as temperature goes down, the water droplets don't freeze right away. Okay. And the reason why they don't freeze, well, it's complicated, but one of the reasons why they don't freeze is that in order to freeze, the ice crystal, we call them ice crystals for a reason, right? Ice is a solid and it's a crystal. And in order for the crystal to form, then the molecules have to assume exactly the right positions within the crystal. This is not immediately obtained, okay? And so, it could be that liquid water particles inside of the droplet are not aligning correctly. Maybe some of them have enough kinetic energy to escape the attraction from the other particles. Maybe the droplet is not homogeneous. The thermodynamic properties or the kinetic properties of the molecules are not homogeneously distributed. And so the water particle does not form right away. The ice particle does not form right away. What you end up having is what we call supercool droplets or supercool liquid droplets, okay? These can actually be cool to very, very low temperature. You can actually have, as it said here, supercooling below minus 15 Celsius is not uncommon, even minus 20 Celsius, which is a lot, right? So when do these freeze, or why do they freeze? Well, sometimes these droplets would happen because there's a supercool droplet that is kind of falling, let's imagine it's suspended in the air. Then there's an ice crystal, and the ice crystal hits this droplet. We'll see videos later on where we'll talk more about ice. This contact is enough to completely freeze this droplet, because if we magnify this, when the ice crystal, here you should imagine all the different molecules, hits the droplet, this touching of the crystal is enough to force the first, let's say that this is the droplet, to force the first molecules on the edge to assume the right shape like the crystal, and this would cause other molecules to assume the shape, and so forth, right? And so then you have, it's almost like a catastrophic behavior, right? It's like it suddenly expands everywhere, and these droplets freeze almost instantaneously. We should also say that, I don't know if you ever thought about this, but ice is extremely complicated. We will not spend too much time talking about ice, precisely because ice is incredibly complicated, and very little is known about ice compared to liquid water. And so why do ice crystals form? That's even still kind of unclear, okay? Something similar to what happens for liquid droplets happen for ice crystals in the atmosphere. So for the water droplets, we had those dirt particles called CCN, and they facilitate the formation of the cloud droplet. In the case of ice, something similar happens, and you have what we call ice nuclei. Again, very little is known about ice nuclei, but essentially they have a similar function. All right, so let's say that they have a similar function to this. So maybe there's some kind of a weird particle, and this particle, when it touches a supercool liquid droplet, it forces this droplet to assume, or the molecules in this droplet to assume, the right positions that they would have in an ice crystal. And when the temperature is low enough, boom, the ice crystal is formed. Okay, so ice, much more complicated. Just to give you some numbers, CCNs, obviously, as you could imagine, they're really, really small. And so we're talking about 0.1 microns of radius. We have about 1 million per liter, which is quite a lot. And also, because they're so small, their terminal velocity is almost negligible. It's very, very small. What does this mean? Well, it means that they can stay suspended in the air for a long time, all right? Precisely because they fall with such small speed. Cloud drops have radii of about 10 microns, 10 micrometers, and their terminal velocity is starting to be quite significant at 1 centimeter per second. So you should imagine clouds kind of falling at 1 centimeter per second, except that that doesn't happen usually, because if you're thinking about cumulus clouds like the ones that we have here in Hawaii, puffy cumulus clouds, right? So their droplets inside would be settling at 1 centimeter per second. Excuse me, made a mistake. At 1 centimeter per second, right? Let me write 1 centimeter per second. But the current of air that we call updraft that sustain the cloud and form the cloud, this has velocities of about 1 meter per second, okay? And, therefore this wins, and this is why clouds are not falling. However, when you start forming large cloud drops, for example, these have radii of 50 microns, then, well, this is starting to be quite a significant fraction. Raindrops, we're talking about millimeter, if not more. Terminal velocity is quite significant. In this case, is 6.5 meters per second. It's like 10 miles an hour. Okay, and so the fall velocity of raindrops, as I'm sure all of you, probably imagine, is a significant figure. Okay, so let's start talking about the nucleation of water a little bit more, and let's start to get sort of quantitative with nucleation. So, excuse me, I had to drink a little bit. Okay, so what happens is that when you have enough water vapor molecules in your atmosphere and you reach the conditions of saturation, okay, as we said, it's not immediate that these molecules would stick together and form a droplet, right? Because on the one hand, you have the mutual attraction between these molecules and, well, the fact that you are at saturation. But on the other hand, surface tension is going to push the molecules away. And so when you are growing a liquid water particle, there's a fight between these two tendencies, right? One that would want you to grow as a liquid water particle, a droplet. The other one that would want you to evaporate. When a balance between these two is reached, we talk about equilibrium, okay? And this is where homogeneous nucleation then can happen, and it favors the expansion of the liquid droplet, and the radius where this happens, this is called RC, is called critical radius. Critical radius. Okay. This is where the two tendencies, surface tension that would want to push people away, this is sigma usually denotes surface tension, and the supersaturation that pushes water vapor molecules inside of the droplet, these two are equal. If you're at radii smaller than the critical radius, you're not growing. The droplet would disappear in a short amount of time. If you're at a radius greater than the critical radius, then you'd want to grow. Okay. How do we compute the critical radius? Well, we'll have to go back to our good friend, the Gibbs energy. Okay. Let's suppose that we have a box with water vapor molecules inside. At time equals 0, it's all water vapor. Okay. So we can define Gibbs energy at initial time. This would be the product of the mass of the gas, okay, times the specific Gibbs energy, okay. At a later time, so this is at t equals 0. At time t, you'd have some molecules have stuck together and they formed liquid water particles. Some are still in a vapor form. So there are MW particles well, or a mass equal to mW of liquid water, and mv is still in the vapor. Remember, originally this was m, okay? And so by mass conservation, m has to be equal to mv plus mw. So far, nothing too complicated. The final Gibbs energy of the system will be a sum of two terms. This is quite intuitive. It will be the mass of the water vapor times the specific Gibbs energy for the vapor, the mass of the liquid water times the specific Gibbs energy for the water, plus this term. What is this term? Well, I told you that there's also this surface tension, right? And surface tension is going to be associated also with an energy, right? And this energy is the energy that you need to overcome in order to go into the droplet, right? You need, if you go at low energy, you'll bounce back. But if you have enough energy, boom, you can go inside of the droplet, okay? This energy, we write it as a product of two terms. Sigma is called surface tension, and it's an energy per units of, it has a unit, excuse me, it has the energy of, it has the units of energy per area, over area, okay? Times A is the area of your droplet, which could be anything, okay? We don't want to assume that it's a sphere yet. Excellent. The change in Gibbs energies is pretty simply computed, and this is simply the difference. The change in Gibbs energy due to the formation of the droplets is simply given by GW minus GV MW. So it's simply just take the difference between these two, and the difference would be GV MV minus M, but MV minus M is minus MW, okay? So this is minus GV MW by mass conservation, and so you put these two together, and you have, let's go to the next slide, and you have the difference between the two specific Gibbs energy. So difference between these two times the mass of the liquid water particle plus sigma times A. This is, pretty simple. Now, assuming that the nucleation happens at constant temperature, we go back to the definition of specific Gibbs energy that we gave a few classes ago, and we're assuming that temperature doesn't change, and so infinitesimal changes in Gibbs energy are equal to the specific volume times dP. dP is the partial pressure of the gas. In this case, it's water vapor. And so what is dP? What is this P? It's simply, you guessed it, the water vapor pressure, okay? Our good friend dE. Okay, so you take the differential of all this stuff. And this differential is simply given by, you take the differential of GV minus GW, and because of this, pressure is obviously the same. This is going to be V of the vapor, specific volume of the vapor minus specific volume of the liquid water times dE. Remember, the specific volume is the inverse of density. Density of the water is 1,000 times the density of the water vapor. So their inverses mean that when you take the inverse, this means that this is a lot smaller than this. And so we can approximate this to 0. So this is simply specific volume of water vapor times dE, the partial pressure of the water vapor. And remember also the ideal gas law, E equals to V RWT. Remember specific volume, okay? And so specific volume is E over RWT, right? And so you can simply plug this back in. Wait. Sorry, my bad. The specific volume is on this side. Yeah, sorry. Specific volume is on this side because otherwise it would be the density. Yes, absolutely. My bad. I apologize. Sorry, something was not. Okay. So we divided, here there was the volume, we divided by the mass, and it becomes a specific volume. Okay. Now everything is okay. RWT over E. And so you plug this back in, and you have the differential between these two is simply RWT dE over E. But now we're assuming T doesn't change, right? T is constant temperature. So T is unchanged. This is a constant. This can be integrated pretty easily. This just gives back GV minus GW, difference in specific Gibbs energy. And this is the logarithm of the differences between the two. Obviously, we're taking into account, we're going from a case where we have where we are inside of the box, okay, and the gas is a certain vapor pressure E, and we go close to the liquid water droplet where the vapor pressure equals the saturation vapor pressure, and that's why we have E over E star. Okay, excellent. Now we can do a few more calculations. Now, if we look at this, excuse me, I went back a little too much. Okay, so we have this part here is covered. Okay, now we have to compute these two. And in order to compute these two, we need to, so yeah, this is covered. We need to compute this stuff, this guy here, MW, and we need to compute this. Okay. Here, now we assume that the droplet is a perfect sphere and it has constant density. In that case, MW, the mass, is simply 4 over 3 pi r cubed, the radius of the particle, times the density of liquid water, and the area is 4 pi r squared, where this is the radius of the droplet. Remember, volume of a sphere and area of a sphere. Plug everything back in, and this is what you should be getting at the end of the day. And when we are at equilibrium, the Gibbs energy reaches a minimum, and therefore this delta G equals to 0. Pardon me, this delta G is at a minimum, okay? And so we need to take the derivative of this and put it equal to 0, okay? Because this is how the minimum is achieved. I hope you remember a few classes ago we said that during phase transitions, Gibbs energy reached a minimum. And so you can turn this around and say the minimum is reached when this phase transition is happening, right? And so we know that the phase transition is happening, and so we're asking, where is this minimum achieved? Okay, I hope this is clear. And if you take this derivative, it's pretty simple. This becomes minus 4 pi r squared rho w t logarithm E over E star plus 8 pi r sigma over 0. R cancels the square. This cancels the 2. The pi's, interestingly, both cancel out. And so then it's very simple to see that R, the critical radius, where you reach the equilibrium, is the 2 sigma that are in this term over all this stuff. Rho W, there was also, an RW that I forgot. Rho W, RW, T times the logarithm of E over E star. Okay. This is the critical radius. A radius higher than that, radius bigger than that, the droplet will grow automatically. Radius smaller than that, the droplet will decrease. Notice that what did I want to say? Okay, yeah, never mind. This is also known as the Kelvin's formula, okay, and allows us to find the critical radius. Excellent. Okay, we can also turn this around and say that starting from the critical radius, we can also figure out how sort of what is the equilibrium vapor pressure for a droplet of a given radius. So inside of the box, okay, the vapor pressure is at saturation, right? Because this is what we assumed. And E was the vapor pressure on the droplet. Now, what is this vapor pressure? Well, you can take this formula and you can, starting from here, instead of finding R, you can solve for E, and what you end up is something like this. So E equals E star, saturation vapor pressure, times this exponential, where B is a factor, as the dimensions of a length scale, 2 sigma over rho W RW times T. Okay? Excellent. Okay, so at equilibrium, we can either find the radius, which is the critical radius, or we can also find the vapor pressure on the droplet. Okay. Notice that if the droplet, if instead of a droplet we had simply a body of ocean, right? A body like we had like a flat surface, like an ocean. Okay. Now the radius of the ocean, let's assume for a moment that the Earth is flat. The radius of the ocean would be infinite. And so you'd have 1 over b over infinite. This would be 0. E to the 0 is 1. Okay. And so you'd have that E equals E star for that particular case. Okay. So this you could think of as a curvature effect in a way. Okay. A factor that is due to the fact that your droplet has a finite radius and it's curved. Okay, this is something that if you went to infinity, you would not be experiencing. Okay, but let's talk about heterogeneous nucleation now. What you see here on the right-hand side, these are actually really, really small ice particles or ice crystals. These are sort of images that you can get with very sensitive electronic microscopes. You wouldn't be able to see all these details. You should not think that this is what ice crystals look like in general, because they don't necessarily. Ice crystals have different shapes, and we'll talk about that. They have different shapes according to the temperature at which they form. Okay, so in certain and pressures at which they form. So in certain conditions, they look like cubes, but they don't necessarily always look like cubes. Okay. Okay, excellent. So how can we say something about heterogeneous nucleation? We will start imagining that we have some substance, some kind of a salt, for example, is dissolved, right? And so we have what we call a solution, where we have a solvent and a solute. And we have water, which acts as a solvent, and then we have some kind of salt, which could be sodium chloride, which is standard salt, which act as a solute, okay? In this case, we would use a chemical law known as the Raoult's law, that tells us that the ratio of the equilibrium vapor pressure over a solution, we'll call this E prime, to the vapor pressure over a pure solvent is equal to the molar fraction of the solvent in the solution. Okay? The molar fraction is just the number of moles of a particular, of the solvent over the mole of the solution. Let's see quantitatively what this looks like. So E prime over E, vapor pressure over, vapor pressure over the pure solvent, over a particular solution, okay, is E prime. E is vapor pressure over a pure solution. This is the number of moles of the water, and this is the total moles of water plus the salt. Okay, and this is quite powerful because now we can simply determine, what these look like. We can compute the new E prime when we have some salt that is dissolved. This is usually NW is something that we can compute because we know the radius of the particle, for example, of the cloud droplet. But N salt is something that is a bit more complicated to determine, and we compute it like this: the number of moles of a particular solute of a salt in the droplet will be proportional to the mass that is dissolved. And then there are two different quantities. I is the degree of ionic dissociation, and phi salt is the molecular weight of the salt that we're taking into account. Okay, with these three ingredients, we can simply compute N salt. Okay, and W, this is pretty simple to compute. The mass of water over the molecular weight of the water. This we can compute again. 4 over 3 pi r cube times rho W over phi W. Okay? Put everything together, and what you end up having is, because NW is at the denominator, you have an r cube at the denominator, and at the numerator it's just a bunch of stuff that has the dimensions of a volume. Okay. Yeah. And obviously C depends on what salt that you're using, of course. Okay. So if you put all this together, go back to the Raoult's law, and you have E prime over E equals, very simply, 1 minus C over R cube. Okay. And C, it's something that you can simply compute. 3I m salt phi W, 4 pi rho W phi salt. Combine everything together. Now remember that E was E star times exp B over R, right? And so you can substitute it in here, and you just end up with E prime over E star. Well, it's written there, so why am I doing this? E prime over star equals this term that is due to the solvent times E to the B over R. Okay? Sorry, I keep mixing solvent and solute. This is due to the salt, okay? The CCN, if you will. Notice that it has a minus sign, meaning that because thanks to this, the vapor pressure is actually diminished, okay? And so it can make it look like when you go close to the particle where the CCN is included, this term, because it has a minus, it can make it look like there's a higher supersaturation. Okay, there's a lower vapor pressure. Okay, which is another way of saying it. Okay. Also, this goes without saying, when you have that R is a lot bigger than B, okay? So in this limit, then you can expand the exponential, okay? As then we can actually do the calculation. It'll be 1 minus C over R cube times 1 plus B over R, okay? And this would be 1 plus B over R minus C over R cube. And then that would be the minus BC R to the 4. But we're assuming that R is big enough that this could be ignored. Okay, so we have these three terms. And so now it's a very simple formula where you have this term that is due to the curvature effect, if you will, so the surface tension, and this term that is due to the presence of the CCN. We can tabulate this. obviously E prime over E star is the sometimes we call it the saturation ratio, okay? And saturation ratio S here would be E prime over E star. And sometimes we call supersaturation S minus 1, okay? And now we can plot these curves, okay? The dashed curve here, this is 1 minus B over R cubed. This is saturation ratio as a function of the droplet radius. Notice that this is a linear scale. This is a logarithmic scale, okay? And this is the Kelvin formula. Unfortunately, here we're using different letters. So A is what we call B, and B is what we call C. But just keep in mind. So this term, Raoult's law, tends to give you lower saturation ratios, okay, at smaller radii, whereas the curvature term would tend to give you greater saturation ratio, okay, meaning that equilibrium, in this case, equilibrium is reached at a much, much lower vapor pressure. Here it means that equilibrium is reached at a much, much higher saturation ratio or much, much higher vapor pressure, okay, that you need. Here you need a lot of supersaturation. Here you don't even need supersaturation, okay? Obviously, these two things are happening at the same time, and so, as you could imagine, there's probably a happy medium, and this happy medium is exactly this point here, right? This maximum point here is the critical radius, okay? Once you are below this, then you tend to decrease the size of your droplet. Once you're above this, then you tend to increase the size of your droplet, okay? Compared to the case where you have only homogeneous nucleation, now you need much, much less supersaturation in order for the drop to be in equilibrium with its surrounding environment. Now, a few words on the atmospheric condensation nuclei. Well, there are a lot of particles in the atmosphere, all right? We call these typically we call these aerosol particles. And some of these, although not of them, some of these are hygroscopic. These can form by a variety of processes. There can be volcanic ash. Some of these are a result of complicated chemical reactions, or maybe the disintegration of some solid, the weathering of rocks, you name it, okay? Typically, the ones that are formed by condensation, because different gases or a gas or a liquid or different liquids came together and formed this particle, they tend to have a spherical shape. But the shapes can be the most disparate. I don't know that I pronounce it correctly, but they can be the most varied, if you will. Some of these aerosol particles are hygroscopic, and so they can act as cloud condensation nuclei. They can be really, really small, like a nanometer, and they can be really, really big, like 10 micrometers, like large salt particles or dust particles or whatnot. A bit of terminology: when these particles are greater than 2 microns, then we talk about giant aerosols. Katie's interested in giant sea salt aerosols. Okay, so these would be in the category. We talk about large aerosols when we are between 2 microns and 0.2 microns. Anything smaller than 2 microns, 0.2 microns, excuse me, is called an Aitken particle. Okay. Okay. And final thing I wanted to say today. Obviously, no two areas have the same cloud condensation nuclei or the same, atmospheric condensation nuclei. Usually, these concentrations vary in space, they vary in time, they vary whether you are, in a desert region, whether you are in a city. For example, here, this is density of particles, so a number per centimeter cube over radius of the particle, and these are various distribution forms. In a rural area, this is a very difficult word for me to say. In a rural area, you tend to have relatively small particles. So there's a mode here. There's another small relative maximum here, and then it kind of drops down. In an urban setting, because you have more pollution, you can have more particles at slightly higher radii. In the desert, just because dust particles can be much bigger than the soot and the pollution that is generated, then these distributions don't fall off quite as strongly. In the polar region, these polar regions tend to be relatively clean and so forth. We talk about accumulation mode between 0.1 micron and 1 micron. Coarse particle mode between 10 microns and 20 microns. And nucleation modes, anything lower than, I would say, 10 nanometers or 0.01 micron, okay? I think this is pretty much what I had to say. So just keep in mind heterogeneous nucleation and homogeneous nucleation. Homogeneous is a lot harder to happen because of surface tension, but the presence of dust, salt, particles, and whatnot in the atmosphere can make heterogeneous nucleation possible. Heterogeneous nucleation is possible because the presence of the salt or whatever hygroscopic particle reduces the vapor pressure. And so kind of reduces the supersaturation that is needed in order to reach equilibrium. So just keep these concepts in mind, keep in mind what cloud condensation nuclei are. Just keep in mind some of the basic scales, basic orders of magnitude that we introduced today, and obviously keep in mind the math that we talked about. This is all I had to say for today about the formation of cloud droplets. As usual, let me know if you have questions. Call me, drop me an email, call me on Skype, anything, and I'll be more than happy to help. Thank you very much for listening, and I will talk to you for the next lecture.